Hello, everyone. The title of my talk is Quantum Jensen-Shannon Divergences between Infinite-Dimensional Positive Definite Operators. So the outline, first I will review the finite-dimensional setting of the Quantum Jensen-Shannon Divergence, the QJSD, and then we'll talk about the unfair QJSD that was developed recently, and then we'll talk about the infinite-dimensional generalization of these concepts to the setting of positive definite choice class operators. So first, the background, I will talk about the QJSD, the quantum Jensen-Shannon divergence. So first, this was developed for density matrices back in 2005. So it's defined by the von Neumann entropy as A. So the QJSD of AB is equal to S of A plus B over 2 minus a half of SA plus SB. So this is also valid for Hermitian positive definite and semi-definite matrices as well. And it has a lot of applications apart from quantum information theory. It has applications in graph theory and in network theory and so on. So this is a symmetric divergence on Hermitian positive semi-definite matrices. And so it recently it was also shown to be the square root of this is actually a metric on the set of Hermitian positive semi-definite matrices. So recently, it was also generalized with something called the unfair quantum Jensen-Shannon divergences. And so it's defined with the parameter alpha. So instead of the Shannon, the von Neumann entropy, we have the α-Tsallis entropy. It's alpha. And so it's defined by J sub A alpha minus J sub A over 1 minus alpha, where alpha is between 0 and 2. And when alpha goes to 1, because we recover the von Neumann entropy. And the square root of this quantity is also a metric for alpha between 0 and 2. Now we have to show that when alpha is equal to 0, it's actually degenerate because it's all equal to 0. And when alpha is equal to 2, it's actually just a Fredholm distance square. So now we can actually generalize this to the case for all alpha belong to R. So we can have something called the alpha quantum Jensen-Shannon divergence or QJSD for all alpha belong to R. So we actually just add a multiplicative factor 1 over alpha to the expression, so as S alpha A plus B over 2 minus a half of S alpha A plus S alpha B, and where alpha is equal to 0 and 1. And then, so we have this kind of multiplicative factor 1 over alpha minus 1 alpha here. And we take the limit when alpha goes to 0 and when alpha goes to 1, and these limits do exist. Now, so this actually has a very close connection with the Log-Determinant divergences. Okay, the alpha Log-Det divergences given by this formula here, and so this is actually this corresponds to the Rene and Kullback-Leibler divergences between zero mean Gaussian measures and Rn, and it's a symmetric measure divergence if and only if alpha is equal to 0. In this case, it's going to be also going to log the S divergence. So this is closely related to the alpha QJSD. Because we have, so the QJSD alpha is valid symmetric divergence for all alpha belong to on the set of Hermitian positive definite matrices. And then when alpha goes to 0, essentially we just recover the 0 Log-Det divergence or the S divergence. And when alpha goes to 1, we recover the standard QJSD divergence. And when alpha equal to 2, we recover the a half out of the square Fredholm distance. So it's kind of a family of divergence that connects 3 well-known divergences together. And so it's so now we know that the square root of this QJSD alpha is symmetric for alpha between 0 and 2. And then when alpha is between less than 2, then the square root of this QJSD alpha is actually Hilbert's square distance on any set of Numerical matrices in the set of symmetric Hermitian positive definite matrices. That is, there is a Hilbert space F and a map phi alpha from simplest N to F, so that the QJSD alpha AB is just a square distance in this Hilbert space F. And moreover, in the special case, density matrices, in particular in the case when we have 2 by 2 density matrices, then for alpha between 0 and 2, we actually have this QJSD alpha is Hilbert's distance on the set of density matrices of size 2 by 2. It follows from the general result using the operator convexity, due to Cullen leap and Schrödinger, and was proved by velocity in 2021. But in general, it's actually not true on all of positive semi-definite matrices of psi 2 by 2, because actually we can find counterexamples for alpha equal to 0 and alpha is equal to 1. So now let's try to generalize this formulation to the infinite dimensional. We care about the case when H is an infinite dimensional separable space, and we talk about the set of positive part operators on H and the Chase class operator on H. So then we want to generalize QHS the alpha of A, B to the case where A and B belong to self-adjoint positive Chase class operators. So let's suppose that A is a self-adjoint positive Chase class operator value or arguments along with K and normalized eigenvalue vectors EK. And we can define A alpha and log of A using the spectral decomposition. And we can see that A alpha is only guaranteed to be in Chase class, where for alpha is greater than or equal to 1. Log of A is unbounded because actually the limit of log of A is if it goes to infinity is equal to 0, and then A of alpha is unbounded when alpha is less than 0. And so this Tsallis entropy is only generally defined only for finite only for alpha greater than 1. And even when alpha is equal to 1, the for Neumann entropy it can be in the infinite. So the resolution for this is that we define something called the positive definite Chase class operators and extended trace. So we consider the set of extended trace class operators defined by A plus gamma I, where A is a Chase class and gamma is equal to I. And then on this set, we define the extended trace to be Chase X of A plus gamma is equal to Chase A plus gamma. So by this definition, we have the Chase X of the identity operator is equal to 1, in contrast to this, the Chase of Chase I is equal to infinity. So with this, we define the set of positive definite operators, Chase class operators. So the eigenvalues of positive definite operators are bounded below by a constant MA. And so we define the set of positive definite Chase class operators as follows. So it's a setup for the form A plus gamma I greater than 0, where A is self-adjoint Chase class and gamma is in R. And with this definition of the positive definite Chase class operator, then we have A plus gamma I to the power alpha is always well defined, because this is always because this is the all R belong to R, because this is always bounded. And then the log of A plus gamma I is also well defined for of all operators of A plus gamma I in this set, and the extended trace is always finite. We can extend the extended trace of A plus gamma I to the power alpha, and then we can define the extended trace of log of A plus gamma I. So everything is well defined. And then along with this, we can also define the extended Fredholm determinant. Remember that with the Fredholm determinant were the formula of the operator from A I plus A. Now we can also extend it to the case when we have, instead of I plus A, we have A plus gamma I for gamma not equal to 0. So we can define where gamma from that I plus A for gamma. And for positive definite Chase class operators, we can show that log-Det X and A plus gamma I is equal to the extended trace of log of A plus gamma I, which is the generalization of the log-Det A is equal to trace of A for a positive definite matrix A. And to see whether this makes sense, we can check actually for example of the Kullback-Leibler divergence, the generalized version of the Kullback-Leibler divergence. So in this case, consider the formula for the Kullback-Leibler divergence between two Gaussian densities in Rn. So this is always modified as a closed form formula. This is not so for gamma. So this is always modified. For gamma and mu belong if being Gaussian measures on the Hilbert space H. With image equal to infinity, then this K on the nu and mu is only less than infinity if nu and mu are equivalent measures. So this this formula is only well defined in special cases. So now to define for all Gaussian measures on H, we can define the regularized Kullback-Leibler divergence by adding a regularization factor gamma here, so C2 plus gamma I, and the log-Det divergence of C1 plus gamma I, C2 plus gamma I, with the log-Det divergence differentiating the extended trace and the extended Fredholm determinant. This is always finite, and it's a valid divergence. And so this one is, instead of the trace here and the log-Det, we have the extended trace and the extended log-Det. And so we can show that for two equivalent Gaussian measures on the Hilbert space on H, when gamma goes to 0, the regularized Kullback-Leibler divergence between gamma and mu will go to the exact Kullback-Leibler divergence between mu and mu. So this is the case when they are equivalent, and we test the first one formula. So this is actually show that actually the kind of this extended trace and the extended determinant actually do make sense. So now, using the extended trace, we can define the extended Tsallis entropy. So the α-Tsallis entropy, the extended version, defined on the side of extent, and the positive definite trace class operator is defined as follows. So we define by extended trace of A gamma I to the power alpha minus the extended trace of A gamma I. So we just replace the trace by the extended trace. And we also have the limit when alpha goes to 1, it's equal to the extended trace of A, negative extended trace of A gamma I log A gamma I. And so now we can define, with the extended Tsallis entropy, we can define the alpha quantum Jensen-Shannon divergence for positive definite trace class operators. So we can define between A plus gamma I and B plus gamma I, where alpha is not equal to 0 and alpha is equal to 1. So it's given by precisely the same form, except that we have the extended trace and the instead of the trace. So the formula is actually exactly the same. And then we have we also have the limit when alpha goes to 0 and alpha goes to 1. These are already codified. And it's given precisely in a very similar form as before, except that we have the extended determinant and the extended trace. So it's a valid divergence on the side of positive definite trace class operator, and it's symmetric, and it's also unitary invariant. So if we multiply both A plus gamma I and B plus gamma I by a unitary operator, it's a linear invariant. And so the square root of this when alpha between 0 and 2 is symmetric on the side of positive definite trace class operator. And the same when alpha less than 2, then on any side of commuting operators is a Hilbert space distance. And when alpha is equal to 2, actually it's just equal to 1 over 8 of the Hilbert-Schmidt distance square. And its continuity in the trace norms, the trace class norms. So when we have, if AN approaches A in the trace class norm and BN approaches B in the trace class norm, and we have basically QJS alpha AN plus gamma I, BN plus gamma I approaches C, QJS alpha plus gamma I plus gamma I. Now, there's one setting in which we can actually have this, like, have some formulas for this, which are computable. So this is a setting of RKHS reproducing Hilbert space covariance operators. So suppose we have data matrix sample according to a probability measure rho on the into space X with n observations. Suppose we have a positive definite kernel K with the reproducing Hilbert space, or RKHS space K with a feature map V from X to HK. Then assuming that the second moment is finite, then we can define about a linear operator Vx. Basically, it's just given by this formula here. It comes as an infinite feature matrix Vx1 up to Vxm. And with this, we can have, with the switcher map, we can define the theoretical RKHS mean. It's just a mean of feature map Vx. And we can define the empirical mean. It's a summation of the average of all the Vxi. And then we can define the covariance operator as well, Cv. Of the feature map of Vx, and we can define the empirical covariance operator of this matrix, basically infinite matrix, feature matrix Vx. So it's a trace. So these are positive trace class operators. And so for this, we can show the divergence QJS the alpha between Cvx plus gamma I and Cvi plus gamma I as cosine formula in terms of the m by m Gram matrices. But the prime matrix is KXI, just given by KXI change equal to KLXI XJ and KYI IJ, which is equal to KFYI YJ. So this is kind of n by n matrices. And so just to show you that actually we have a cosine dominant. So in this case, for example, if we have, this is the case when alpha is not equal to 0 and 1, so it has a cosine overlay in terms of the grand matrices. So this is the grand matrices here. And so we have it's expressed in terms of the trace. When alpha is not equal to 0 and 1, so the trace for our alpha. And in the case when alpha is equal to 0, of course, we have the expression in terms of the log-Det. And in the case when alpha is equal to 1, we have the trace log and of the grand matrices. So these are your cosine formulas. So this is a very simple example where we're going to compare RKHS covariance with the generated by Gaussian mixtures. So here we have two data matrices X and Y, but generated by the same Gaussian mixtures on R5, so random Gaussian mixtures. And so we have with the Gaussian KXY, and so we have two RKHS covariance operators associated with these two data sets, two data matrices, and we can compute the QJS, the alpha between them. So this is like alpha from 0. This is alpha from 0. We have the log-Det, where this is when alpha equal to 0.5. This is when alpha is equal to 1. This is the standard quantum QJS, the Shannon divergence, and this is when alpha is equal to 2. We have the Hilbert-Schmidt square Hilbert-Schmidt distance. And so they all converges to 0 because it's they represent the same probability distribution, namely the same Gaussian mixtures in R5. So this is an example to show that they can be computed, everything can be computed explicitly. So in summary, we talked about the alpha quantum Jensen-Bregman divergence, the positive definite emission matrices, and we talked about the infinite dimensional generalization. So between positive definite trace class operators. So this is done via the extended trace and the extended Fredholm determinant. So I talked a little bit about the application for the RKHS covariance operators. Of course, in the future, we're going to explore the future applications as well. And then we have of course, even in the finite dimensional setting, we're interested to study the case of the Hilbert space embedding density matrices for dimension greater than 2, because now we have results which is dimension greater than 2. So thank you for listening.